Imagine this. A doctor, maybe it's a radiologist, right? They're looking at screen after screen of complex medical images, an X-ray, an MRI, maybe even like a video from an endoscopy. And then somehow they've got to pull all that incredibly detailed visual information together and then draft this clear, concise, clinically spot-on report. That report. It guides the patient's entire care plan. It's a huge mental load, isn't it? So today, we're diving deep. We're plunging into the really fascinating world of multimodal generative AI for medical image interpretation, or GenM for short. This is an area of AI that's moving incredibly fast. It's not just about helping out. It seems poised to, fundamentally change how those vital medical reports get made.
Exactly. And our mission today is really to unpack that. We want to look at how GenMI actually works, explore its, frankly, incredible potential to shake up healthcare, but also, critically, look hard at the very real hurdles, the big challenges that we still need to get over before it can truly deliver on all that promise. We'll get into the tech underneath, talk about applications across different medical fields, some might surprise you, and introduce this really groundbreaking idea called the AI resident.
Yeah, get ready for some real aha moments, I think, because we're about to explore how these advanced AI systems could soon be assisting doctors, assisting patients in ways we're maybe just starting to imagine. Okay, so let's kick off by really getting a grip on the problem GenMI is trying to solve. Why is interpreting all these medical images and then writing up those reports, why is it such a heavy lift? For the system, sure, but also for the clinicians doing the work.
Well, it's precisely that translation challenge you described. Think about it. You're taking this incredibly complex visual stuff, X-rays, MRIs, even moving endoscopy videos, and you have to turn it into insightful, useful, written text. And that report, that text, it's absolutely crucial. It's how findings get shared, how patient care gets directed across so many specialties, particularly for radiologists. The demand is just, well, it's exploding. Partly because we have all these amazing advanced imaging tools now, like CT and MRI. But each one needs very specialized expertise to read correctly. Let me give you a more concrete example. Imagine a cardiologist trying to get the full picture of a patient's heart health. That's rarely just one image, right? It could mean pulling together info from cardiac angiograms, perfusion studies, cardiac MRI, echocardiograms, cardiac CT scans, all of it. Now, synthesizing all that very dense visual data into a coherent, concise, and clinically accurate summary, that's an enormous challenge, even for the most experienced human experts. And honestly, that complexity often means some information just inevitably gets lost. The human brain can only juggle so much. Then you add in the growing shortage of specialists who are skilled in reporting these complex things. And what you get are delays. Delays in getting reports back, and worse, errors. Errors that can really seriously impact patient care.
Wow, yeah. That paints a very vivid, almost daunting picture of the challenge right now. So, okay, where does AI fit in? What's the actual promise here? Is it just about doing things faster?
The promise is, well, it's really compelling. These AI report generation tools are not just about speed, though that's part of it. They show huge potential to tackle these core problems. They could, for instance, do the initial reads of exams, maybe draft preliminary reports that a human then reviews and refines. Just that step could let clinicians get through cases much faster, significantly cut down report turnaround times, and, importantly, expand access to that specialty-level reporting, especially in remote areas, right? Kind of like an advanced version of teleradiology. And the downstream effect, less stress on the whole healthcare system. But, it goes beyond just efficiency. As these AI models get trained on bigger, better, more diverse data sets, they might actually get better at predicting things, like how well treatment might work, or even spotting diseases earlier. They could also potentially communicate complex health information more effectively, maybe even directly to patients in language they understand. And here's a really interesting point. AI models are incredibly scalable. Think about it like this. Imagine a whole team of expert radiologists reviewing a case together. Collectively, they'd likely be more accurate than any single one, right? Well, AI could potentially mimic that. Some research suggests that using a mixture of AI models may yield greater performance improvements than relying on just one human expert. It's like creating this super intelligent diagnostic team.
Right, I see. So GenMI isn't just a faster image processor. It's about boosting accuracy, making specialized knowledge more accessible, maybe even improving patient outcomes by harnessing this sort of collective AI intelligence. When you think about that promise, what immediate benefits jump out at you? How could this really change things on the ground? Okay, so we've got the problem, we got the big picture promise. Let's pull back the curtain a bit more. Let's get into the nuts and bolts. What is multimodal generative medical image interpretation, GenMI? How does this stuff actually work?
Right. So at its heart, GenMI is a specific field within AI. It's focused squarely on generating medical reports directly from medical images. It's basically bringing together all the latest AI advancements to tackle those reporting challenges we just discussed. The ultimate aim: to match human expert performance in creating these reports across different areas like radiology, pathology, even dermatology. Now, the multimodal part is really key here. It means the AI isn't just looking at one thing. It can process and integrate different types of data together. So not just one image, but maybe clinical history text, findings from previous reports, and eventually maybe even different kinds of images like a CT and an MRI all at the same time. And generative, that means it's not just classifying what it sees or detecting a feature, it's actually creating something new. The text of the report itself, kind of like how a human doctor would write it.
That difference between just like spotting something versus actually writing the report, that feels like a major leap. We hear AI all the time. How has the technology evolved specifically to make GenMI possible and different from earlier medical AI?
Yeah, the evolution, especially recently, has been pretty dramatic. Traditionally, these kinds of systems were often simpler. They usually had two main parts: a vision encoder and a language decoder. You think of it almost like a very specialized translator. The vision encoder would look at the image, pull out the important visual information, and basically turn it into a numerical code, a vector. Then, the language decoder would take that vector and translate it into the words of the report. Image in, text out. Pretty straightforward, conceptually. But the real game changer, the revolution, really came with what we call foundation models. These are these huge pre-trained AI systems that can do many things. The most famous examples are large language models, or LLMs like the GPT series people hear about. Their arrival has just completely reshaped the landscape for medical image interpretation. So now, instead of smaller purpose-built models, a lot of GenMI research uses these powerful LLMs as the language decoder part. Why? Because LLMs bring this built-in knowledge and reasoning ability. They understand language, context, and even some world knowledge, making the generated reports potentially much richer and more nuanced. But LLMs aren't just being used as decoders now. They're also being used for things like report quality assurance. So an LLM might review an AI-generated draft report, rewrite sections for clarity, or, crucially, remove things called hallucinations. Right? These are like mistakes where the AI might confidently mention findings from a previous report that doesn't actually exist. Really important to catch those. The cutting edge now really involves vision language models, or VLMs. These are systems designed to intelligently fuse individual vision and language models together, so they can jointly understand both the image and related text inputs, like the patient history, much more deeply. A well-known example is GPT-4V. It can do things like recognize the type of scan, identify anatomical parts, generate structured reports, even tweak the report based on text prompts. Though it's important to mention, initial studies looking at its ability to make accurate diagnoses found its performance was poor. So its current strength seems to be more in the report generation and understanding, maybe not yet in standalone diagnosis.
Okay, that multimodal aspect, pulling in text history with the image, sounds incredibly powerful. How does the AI actually do that? How does it integrate and make sense of these different streams of information?
Yeah, that multimodal processing is absolutely a key differentiator for these newer GenMI systems. It's not just about the pixels anymore. VLMs can seamlessly weave in other vital info, like the patient's prior medical history or clinical notes. For example, one clever approach involves feeding the model a special textual domain identifier token along with the image. Think of it like a digital tag that immediately gives the AI important context like chest x-ray, emergency department visit, before it even starts analyzing the image. It sets the stage. Now, under the hood, how does this work? Well, techniques like cross-attention are crucial. You can sort of imagine the AI having an intelligent focus. It learns to assign important scores to different parts of the image and different parts of the text. It figures out, okay, this part of the scan seems related to this phrase in the clinical history. Connects the dots. Another key technique is contrastive learning. Here, the model is trained to tell the difference between similar image-text pairs and dissimilar ones. This helps it learn a common ground, a shared way of representing both visual and textual information, which really boosts the quality of the generated reports. And here's something really exciting that's emerging. Most work focuses on multimodal inputs, like bringing different data in. But now, some researchers are exploring multimodal outputs. So the AI doesn't just output text. It might generate the report and something visual alongside it. For instance, some models can draw bounding boxes right onto the original image, highlighting the exact spot that corresponds to a finding mentioned in the text. That makes it way easier to understand and verify, right? Huge for explainability.
There was even one study that explored having the AI generate new X-ray images based on an input. Still early days for that, but very interesting.
Generating new images too. That's,
Mm.
oh, wow. Okay, but with all this power, how do we ensure accuracy, especially clinical accuracy? We're talking about patient health here. What makes these models truly reliable?
Absolutely critical question. Improving clinical accuracy is, well, it's paramount before any widespread use. Two main strategies have shown a lot of success here. First, incorporating external medical knowledge. Some models use what are called memory matrices, basically, ways to store information about how image features map to report text, helping the AI stay consistent and accurate. Others integrate broader clinical knowledge using knowledge graphs. You can picture these as huge interconnected networks of medical facts. Nodes might represent diseases or symptoms, and the connections or edges show the relationships between them. A really well-known one is called RadGraph. It's massive, built from millions of entities and relationships found in chest X-ray reports. Using knowledge graphs like RadGraph has been shown to significantly boost clinical accuracy when generating reports. The second main strategy is explicitly training the models on disease classification. So you don't just train it to write text, you also train it to identify specific diseases or findings in the image. This forces the model to pay closer attention to the clinically important features. Sometimes the disease tags it predicts are even used as a starting point for writing the report narrative. Now, there can sometimes be a bit of a trade-off. You might push for super high clinical accuracy, but maybe the report sounds a little less natural, less fluent, what we call lower natural language similarity. But, with careful design and implementation, it's becoming more and more possible to get both clinically accurate and natural-sounding reports.
Okay, let me try and recap this bit. So GenMI uses these really advanced AI models, foundation models, LLMs, VLMs. They don't just see images, they seem to understand them in context with other data, like patient history. They learn from enormous data sets, often incorporating external medical knowledge, like from knowledge graphs to boost accuracy. And they're becoming more multimodal, not just in what they take in, but also what they put out, like highlighting images alongside the text. This really does feel like a different league compared to older medical AI. Thinking about all these technical capabilities, what aspect excites you the most about what GenMI could actually achieve in healthcare, maybe even soon? All right, let's shift gears slightly. Beyond just churning out reports, the sources talk about this really compelling vision, the AI resident. What exactly is that, and what could it mean for doctors and patients day to day?
Yeah, the AI resident concept is pretty neat. It's proposed as a new way, a new paradigm really, for actually deploying GenMI in a clinical setting. The whole idea is inspired by how things work in academic hospitals, with residents and attending physicians. It's designed specifically to empower both the clinicians and the patients. So its first job, its initial role, would be to specialize in drafting clinically accurate reports. Think of it as providing a really high-quality first draft for a human resident or doctor to review, edit, and finalize. But crucially, it's not static. The AI resident would constantly learn from the human corrections and additions. It gets better over time by seeing how the experts refine its work. And it could really help improve report quality, especially when maybe the initial information is a bit limited. Sparse clinical notes or vague reasons for the exam. Imagine a scenario. A radiologist sees some cavities in the lungs on a scan. The AI resident in its draft might automatically insert helpful prompts like, consider patient immune status. Is the patient immunocompromised? Or query history. Does the patient have a known history of tuberculosis? These aren't diagnoses, but they're smart prompts. They help the human radiologist think through the possibilities and formulate a much better, more complete differential diagnosis right there in the report, tailored to that specific patient. It could prevent important context from being missed.
That sounds less like just a tool and more like a cognitive partner almost.
Yeah.
How would this AI resident empower clinicians and patients more directly, like in their interactions with the medical data?
Exactly. Its real-time interactive abilities are key here. For clinicians, maybe a GP who gets a specialist report, the AI resident could let them probe details. They could ask the AI, show me the exact spot on the MRI that corresponds to the sentence about the lesion. Or vice versa. Click on a region in the image and ask, what does the report say about this area? Think about a surgeon planning an operation. They could potentially query the AI resident for a really in-depth understanding of the anatomy of the region they would be operating upon, visualizing it directly from the patient's scans linked to the report findings. Could really minimize surprises in the OR. And for patients. Now, this needs to be carefully managed, right? under supervision. But patients could potentially interface directly with an AI resident, maybe to get a quick second opinion explained clearly or just to understand their own condition better. Imagine reading a report where you click on a sentence and it highlights the relevant part of your X-ray. Or maybe you see a confusing medical term. You could ask the AI, what question should I ask my doctor about this? That kind of direct, personalized interaction could seriously boost patient satisfaction, maybe even help them stick to their treatment plans better. And then there's medical education. An AI resident could provide real-time and personalized feedback to medical students or trainees. Students could use it to compare similar cases from a huge library, see the whole spectrum of how a disease might look, or even get feedback on the reports they try to write. It could be an amazing supplement to traditional training, always under the guidance of an attending physician, of course.
So collaboration seems absolutely central here. It's humans and AI working together, even learning from each other. How do we make sure this AI actually aligns with what humans want and need? How do we make it work with people, not just alongside them?
Yeah, that human input, that alignment is absolutely critical. And interestingly, studies are already showing that when clinicians review and edit AI-generated reports, the final versions are often rated as comparable to or even preferred over reports written entirely by clinicians. Hmm. So the synergy is already showing promise. Techniques like reinforcement learning from human feedback, RLHF, and direct preference optimization, DPO, are being used technically to fine-tune these models based on what doctors find helpful and accurate. And looking ahead, there's real potential to even involve patients in this alignment, maybe adapting reports to use less medical jargon and more straightforward language based on patient feedback. But the learning isn't just AI learning from humans. It can go the other way, too. Clinicians can definitely learn from the AI. For example, if these models get better, they could potentially offer feedback on subtle diagnostic misses, maybe using those multimodal outputs to highlight an area on an image a human might have overlooked. And the AI's ability to sift through vast amounts of data, that makes it an incredible tool for clinicians facing a tricky case. They could rapidly search for similar past cases. You could even imagine collaborative brainstorming sessions. The AI might offer probing questions based on patterns it sees, suggesting diagnostic avenues a human might not have immediately considered.
Okay, the AI resident idea really does paint a picture of AI as a true partner, doesn't it? Not just a passive tool. It's about empowering everyone, doctors, students, patients. Thinking about this collaborative role, what specific aspect of the AI resident resonates most strongly with you? Why? This all sounds incredibly exciting, maybe even a bit like science fiction becoming reality. But like with any powerful new tech, there have got to be challenges, right? Roadblocks. What are the really formidable obstacles we need to tackle before GenMI becomes widespread in everyday clinical care?
Oh, absolutely. The obstacles are significant. One of the biggest is figuring out the right benchmarks and evaluation metrics. You see, the traditional ways we measure language quality in AI, things like BLEU scores, Meteor, they're okay for judging if the text sounds fluent, like human writing. But they completely miss the mark on clinical accuracy. They don't know if the medical terms are right, if the findings are correct. A fluent report that's wrong is dangerous, right? So researchers are developing new metrics specifically for medicine. Things like RadGraph F1, which checks the overlap of clinical concepts, or RadCliQ, which uses error scores determined by radiologists. There's also RadBench, a benchmark suite specifically for testing these big radiology foundation models. But even with better automated metrics, human evaluation is critical, absolutely essential. We need rigorous studies where real clinicians assess these tools to see if they're truly feasible and safe in practice. And beyond just initial testing, we need to understand the downstream clinical effects. How does using this AI actually impact patient care and outcomes in the long run? We need that evidence before wide adoption. Then there are ongoing concerns. The performance of these large language models can actually change significantly over time, even without explicit retraining. That drift is a huge worry in medicine, and they're vulnerable to adversarial attacks. Someone could potentially manipulate the AI to generate incorrect outputs, maybe specific diagnoses to fuel overprescription, commit insurance fraud, or even falsify results in clinical trials. So constant monitoring and strong security are absolutely non-negotiable.
Wow, yeah. Adversarial attacks. That's scary stuff. Beyond the technical hurdles, what about the people involved? Is there a risk of doctors or patients relying too much on these AI systems?
That is a major concern, yes. On the clinician side, there's a real danger of over-reliance. Doctors might hesitate to change an AI-generated report, maybe because they're unsure about accountability if they edit it and something is still missed, or they could fall victim to confirmation bias, seeing what they expect to see, or automation bias, just sort of implicitly trusting the machine's output over their own clinical judgment. And this could lead to serious problems, like missing rare findings that the AI wasn't trained well on, or just accepting subtle errors that a careful human review might have caught. And connected to this is the huge ethical issue of bias in the training data. This is a big one. Most of the large data sets used to train these models heavily overrepresent people of European descent. What does that mean? It means the AI might produce lower quality drafts for minority populations because it hasn't seen enough diverse examples. If doctors then over-rely on those potentially biased drafts, it could worsen health disparities for already underserved communities. For patients, too, while that direct interaction sounds great, it has to be controlled. Patients shouldn't be relying on an AI for direct medical advice or diagnosis. Any report, any interaction, needs practitioner oversight and approval. Clinicians have a big role in educating patients about how to use these tools appropriately. The fundamental principle has to be that AI is there to bolster clinical care, to support humans. It cannot replace the empathy, the broad contextual understanding, the nuanced judgment that, frankly, only humans can process and provide.
And the data itself, you mentioned bias, but are there other limitations with the data we're using to train these GenMI models?
Yes, definitely. Beyond the bias issue, which is critical, there are other limitations. Deep learning models, especially these giant LLMs, are just very sensitive to the data they're trained on. They learn and can unfortunately perpetuate any biases present in that data. This is worrying not just for reports, but also if these models are used in education, they could pass on flawed or biased understandings. Even using human feedback to improve the AI, while well-intentioned, can accidentally create biased feedback loops if we're not careful about whose feedback is weighted and how. The datasets themselves often have limitations. Take MAL-IQ-CXR, a very popular one. It's huge, but it's limited to unimodal chest X-ray scans, just one type of image. Many datasets are also imbalanced. They might have tons of normal scans, but relatively few examples of abnormalities, especially rare diseases. This makes it hard for the AI to learn to reliably identify those less common conditions. It also limits its use for creating diverse test cases for training doctors. People are working on ways to mitigate this using specific model designs, adding explicit disease tags, creating longitudinal datasets that follow patients over time, even generating synthetic image text data to fill the gaps. Another issue is noisy labels. Sometimes the labels or reports associated with images in the training data aren't perfectly accurate, maybe due to differences between human interpreters or errors in how the data was automatically collected. There's promising research in areas like zero-shot learning, getting AI to recognize things it wasn't explicitly trained on, but the technology still needs more development for medical use.
Okay, and thinking about the sheer variety in medicine, is GenMI actually ready for all the different types of medical imaging, all the different specialties, or is it mostly focused on certain areas right now?
That's a great point. Right now, it's not quite ready for everything. There's been limited work, for example, on applying GenMI effectively to 3D imaging, think complex MRI and CT scans. A big reason is the lack of large, publicly available, well-annotated data sets for these modalities. The ones that do exist are often private, proprietary, and extremely expensive to create or access. So a lot of the research you see on, say, MRI report generation might focus on simpler tasks, like generating qualitative summaries or just filling in predefined templates rather than creating full, nuanced reports from scratch. Outside of radiology, GenMI has shown some promise in areas like ophthalmology and dermatology, but again, we still need more robust data sets and perhaps more data-efficient algorithms before it's truly successful across the board. And then there are the practical hurdles of cost and implementation. Building and maintaining these systems, acquiring the necessary data, it's all very expensive. Public data sets are unlikely to keep pace. There's also a real-world concern that hospitals or healthcare systems might see AI primarily as a way to increase patient volume, push more scans through, rather than focusing on how it can genuinely improve the quality of care. So the key takeaway really has to be implementing GenMI gradually. Maybe start in one area, like radiology, really focus on demonstrating value for patients and improving clinical care. And clinicians themselves need to be vocal to stand up for the primacy of the patient-doctor relationship, making sure technology serves that relationship, not the other way around.
Right. It's abundantly clear that while the promise of GenMI is immense, potentially transforming workflows, improving access, enhancing accuracy, we absolutely have to navigate these significant challenges carefully. Evaluation, human factors like over-reliance, data quality and bias, ethical deployment across different specialties. It's a lot. How do you think we strike that balance? balancing the incredible speed of AI development with the absolute necessity for safety, fairness, and keeping the human element central in healthcare.
Well, looking at the big picture, multimodal generative AI for medical image interpretation, GenMI,
Yeah.
it really does represent a truly promising frontier. There's no doubt about that. It has this genuine potential to ease the burden on clinicians, to broaden access to expert-level interpretations, and to empower everyone involved, doctors, trainees, patients with interactive tools and better understanding.
And as GenMI tools become more common, which seems likely, the responsibility really falls on all of us, doesn't it? Researchers, doctors, the people making policy, and yeah, even us as informed patients. We all need to push for development that's transparent, that's ethical, and that always, always puts improving human health and the human connection first.
So maybe here's a final thought to leave you with. Considering just how powerful this technology could become, what do you think is the single most important ethical safeguard we need to put in place? What's the one thing we absolutely must get right to ensure GenMI strengthens the doctor-patient relationship, helps humanity, and doesn't accidentally undermine the very things we value most in care? Something to chew on until our next deep dive.
Thank you so much for joining us on this deep dive today. We really hope you feel a little more informed, maybe a little less intimidated, and definitely a lot more curious about the future of AI in medicine.